Today we're talking about the law of conservation of energy. And the law of conservation of energy, any conservation law, anytime you see this conservation of anything, all that means is whatever you start with, you're going to end with, in a quick nutshell. So law of conservation of energy, energy can't be created or destroyed, only changed from one form to another. What that really is saying then is whatever energy you start with, you're going to end up with that same amount of energy at the end. So starting energy, finishing energy are the same. Total energy in a system is always conserved, and again, conserved means it's the same or it's constant, same before and after. But while that's true, the forms that the energy take can vary. So we can switch from one form to another, which is kind of what we're saying in the law of conservation of energy at the top. So here's what we can see. So there's the law of conservation of energy, same words. Here's what's going on, and what you can kind of see is right here, this bar here, the total gravitational potential energy, that's what that GPE stands for. Gravitational potential energy. Okay, that's GPE. GPE equals gravitational potential energy. That's this thing. The other one here, kinetic energy. Okay, so those are two types of energy, two broad forms of energy that we're talking about in grade 11 physics. What you can see is as the ball swings back and forth, the amount of gravitational potential energy goes up and down, the amount of kinetic energy goes up and down, but this one here is total energy, and it remains constant. If you were to add up the reddy color here and the purpley color here, if you were to add up those two bars at any moment, they'll always add together to the same amount, so the total energy is always the same. What we're seeing here is kind of like the law says, energy is not created or destroyed. It does change from one form to another, right? It's changing from gravitational potential into kinetic energy, but it always adds up to the same amount. And thanks to Science Joywagon for providing this, whoever they are. What we can say here is total energy then, ET, or they call it TE up here at the top. Total energy is kinetic energy plus gravitational potential. We can see the energy switching back and forth from one to the other, but again, that total energy remains constant. Okay, and we're going to use that idea as we kind of come up with equations and solve problems. We're going to use this idea. Here's another look. You can see that the child at the top as they kind of sled down here. They start off with a bunch of potential. We'll watch this again. A bunch of potential energy. It becomes kinetic energy. And then something happens here, and we'll talk about that in one sec as well. So as it starts again, I want you to keep in mind or keep your eye on this potential energy. Okay, so when they're up at the top, you can see right there, lots of potential energy. As they come down the hill, they're losing height, which means they're losing potential energy, but they're gaining speed, which means they're gaining kinetic energy. Okay, so the potential is becoming kinetic. Here, as they slide across this unpacked or rough snow, they're encountering friction. What we've got happening here then is work due to friction. This thing here, this W, you could say is work done by friction. It's, work done by friction, or work done by any force, I guess, is FD cos theta. FD cos theta. They're sliding forwards, their displacement is forwards. But remember that friction is back this way. The angle between there, 180 degrees. So the work done by friction, anytime you have cosine of 180, that's going to give you a -1. So this thing right here gives you a -1. The work done by friction then is negative FFD. That's why this thing here is on the negative side, because friction's doing negative work. It's removing energy. It's removing that kinetic energy. But you can see here the total mechanical energy is always a constant. If you were to kind of add together all of these energies, you're always going to end up with the same value, except here as the total mechanical energy starts to drop, because the work becomes thermal energy, or the energy becomes thermal energy. The child in the sled loses all the energy. It all goes down into the snow. What that really does is it creates some heat and it melts the snow and kind of packs it down and stuff. So again, the energy is not lost, but it is lost to the child in the sled. And I think I got some words coming here, so let me erase a little bit of this stuff. Let's get rid of that and this. And let's see what else we got on here. So all the gravitational potential energy at the top, you can see from this bar here, all the gravitational potential energy at the top all gets converted into kinetic energy over here. That's the kind of red bar in this thing. At the bottom, as a toboggan hits the loose snow, where does all the energy go? We kind of mentioned that. It all becomes this work done by friction, and this bar down here, that really becomes heat. So it's all converted into work done by friction. It becomes heat energy or thermal energy, which just kind of melts the snow a little. This is a good short answer kind of question. You could run through all these steps. Let's get into some actual numbers though. Let's see how we actually use this idea. So here's a kind of a common or a typical question in grade 11 physics. How fast is the roller coaster going at the bottom of the hill? What we're told up here is, or in this diagram, I guess, there's a bunch of numbers here. I'm not sure actually how fast it's going here. So you could say V at the top. I don't know. We could assume 0, but since they give me a V here and a height here, I'm going to use those numbers. So remember, total energy at any given moment. So total energy at any instant, I'm going to call this position 1, or maybe, yeah, let's call it position 1. Total energy at position 1, so there's position 1, is equal to the total energy at any other position. It's also equal to the kinetic plus the potential energy. So half mv1 squared plus half m, oh no, sorry, not half mv2 squared, mgh2. Getting too excited. Or mgh1 is what I'm trying to say. The total energy at this position is the sum of the kinetic energy due to that speed and the gravitational potential energy due to that height. What we're trying to figure out is how fast is it going down here at the bottom. In order to do that, in order to find that, I also need to know what's the height down here at the bottom. So if we're going to call this height 15 meters, then and the distance from here to here is 15 meters, that means the height down here at the bottom is 0. That's typical. Usually when we do these questions, we'll take the height at the lowest point as our 0 height. What we can say then down here at the bottom is E total at position 2 is half mv2 squared plus mgh2. And just remember, we just finished saying this height is actually 0. This guy's going to cancel out. It doesn't always cancel out. So, keep in mind that it could be there, but in this case, it's gone. It's going to cancel out. The final step to this, or the final piece to this puzzle, is this. What we're told is that energy is not created or destroyed. What we know is that the total energy at position 1 is equal to the total energy at position 2. Okay, so I'm going to go on to the next page. We're going to set this whole thing right here equal to this whole thing right here. We'll sub in some values. So we got the mass, we got V1, we got H1. We know H2 is 0 as well. And we're going to try to solve this thing. And we'll find out how fast it's going at that lowest position. Okay, so just to kind of start from scratch, E total 1 is equal to E total 2. What that means is half mv1 squared plus mgh1 is equal to half mv2 squared plus mgh2. Just stand back and gaze at that for one sec. Oh, what a glorious equation. We just finished saying, though, on the previous slide, H2 is 0. Again, that's not always going to be the case, but in this case it is. We were told the mass was 300 kilograms. V1 was 10. Don't forget to square that. Mass is 300. G here is just the magnitude, okay? Just 9.8. Don't sub any negative signs in when we go through this. Okay, so 9.8. H1, what did we have there? 15. Mass is 300. V2 squared, and then again that last term there plus 0, the mgh2, we don't even have to write that, but that thing is 0 because h2 is 0. Now you might be clever and say, look, there's a 300 in every term. Couldn't we cancel that? The quick answer is yes, but let's pretend we didn't recognize that yet. The first part of this question says do it with mass. Okay, so we're going to do this thing with our mass here. We've got 100 times 150. So this thing gives us 15,000. 300 times 9.8 times, whoops, not 0, but 15 gives us 44,100. This would be 150 V2 squared. Whoops, 15,000 plus 44,100. This is 59,100. We'll divide by 150. We get 394. Square root. We don't have to show all these steps, but I'll kind of lead us through. I'll just turn this around at the same time. So 19.849. V2, approximately, how many sig digs? I guess we'll take it as 2 sig digs. So it's about 20 meters per second. Okay, so here's kind of part A of that question. Just remember the question was asking us somewhere up here, yeah, how fast? How fast is the roller coaster going at the bottom of the hill? We did it with mass. What if I didn't give you this mass though? Or what if you recognized, wait a sec, that 300 is kind of in every term here. It's like right here, it's here, it's here. Could we cancel that thing out? And the quick answer is yeah, for sure. Let's try that. If I repeated this question, and if you were to do a question like this on a test, you don't need to repeat it for me, just do it once. But I just wanted to kind of prove to you, or demonstrate, I guess, that when we write out this big equation, mass is in every term. It's right here, 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 here. We can actually divide both sides by mass and cancel that out. Okay, so this is, just be careful when you do this, right? This is true anytime we use this conservation of energy equation, this big long thing. We can always do this. As long as there's mass in every term, this will work. So if we were to sub in those same numbers, the work is going to look a little different initially. And again, plus 0, this here is gone. It's going to look a little bit different initially, so as we go through and find these numbers, the numbers are going to look a little different. But our final answer is going to be the same. Plus 50 is 197. Times 2. There we go. There's our... Here we kind of start matching up again. V2 then. I'm out of room here, so I'm just going to skip right to the final answer, but we get the same answer. What that means is we do not need to include that mass. What that probably means in most questions is I won't give you the mass. Just to kind of see if you remember to cancel that thing out. Last step on here is, shouldn't we include the rest mass energy? If you included the rest mass energy, so let's say over here, if we said really total energy is half mv1 squared plus mgh2 plus mc squared, shouldn't we really be doing this? And I guess you could say, yeah, the answer is yes, we should. Whoops, this is an mgh1 over here, plus mc squared. The problem is, you can go ahead and try these numbers. The problem is, this value right here is so big that we won't even see these numbers. This value, this mc squared, is just too big. The reason that we're safe to ignore it is because this mc squared and this mc squared are going to be the same. The mass isn't changing, right? It's a 300 kilogram roller coaster at the top and the middle at the bottom. That mass is the same. The speed of light is a constant. That's why it's the letter C for constant. Those things can just cancel out. When we do this in class, I'll probably go through and sub some numbers in, and you can see just how big it is. But to keep this video a little shorter, I won't bother. But if you want, as a fun exercise for you, go ahead and sub some numbers in and see just how big that value is. And then try adding it to these numbers, and you can see your calculator won't even recognize that you've added these numbers on. They're just too small compared with this mc squared. All right, here's some real kind of questions as well that we're going to get. So roller coasters are a common question. Throwing objects, so like projectile type objects, which you could solve using kinematics and projectile motion and stuff like that. You can also do using energy. So when you see this kind of a question in this unit, let's try to use energy. We got Rayon standing on top of the school, 15 meters above the ground. He throws his chemistry textbook straight up at 13 meters per second. Okay, so here's position 1. That V1 is 13 meters per second. Height 1, I'm going to go ahead and call kind of height down here at the ground 0, which means height 1 is just that 15 meters that we were given. He watches, let's see, where is it? He watches as it just clears the edge of the school. So he throws it kind of straight up, but it comes down and it just misses the edge of the school, falls to the ground below. We're going to find a couple things. We're going to find the max height above the ground. So I'm going to call that position 2. And then the velocity of the book as it strikes the ground, we'll call that position 3. Okay, so we're going to find a couple of things here. For part A, I'm going to use conservation of energy. Half mv1 squared plus mgh1 equals half mv2 squared plus mgh2. So that's our starting point, right, for these things. When I do this, if I'm looking for something like what is this maximum height, so what is h2, I need to know sort of the 3 other variables, right? So if I'm looking for this h2, I need to know what's v2, what's h1, what's v1. I've already written down v1 and h1, so I need to know what is v2 before I can solve for h2. Okay, so I always think there's a v and an h at any specific location, and comparing those 2 locations, I need to know 3 out of the 4. V2, we remember this from kinematics. Hopefully you remember this from kinematics. V2 at the highest point is just 0. Okay, so kind of like we did in our last question, one of these things will often cancel out, not always. I gave you the mass of this textbook, but do we need it? Nope. It actually doesn't matter what the mass of the textbook is, right? I'm going to cancel those masses out. What I'm left with then is 1/2 V1 is 13. Remember, G is magnitude, so positive 9.8. Don't put in a negative sign there. G again, 9.8. H2, that's what we're looking for. Okay, so I got to try to solve another question in this space, so I'm going to skip just a little bit of steps here. 13 squared times 0.5 gives me 84.5 plus 9.8 times 15. Okay, so in total, the left-hand side gives me 231.5 equals 9.8 H2. Divide by 9.8. The height, 23.62. For 2 sig digs, we'll say, excuse me, it's approximately 24 meters. Okay, so there is the max height. Max height, and I do want to point out that's above ground. Okay, so just remember, we're kind of saying the height equals 0 is down here. So if height 1 is 15, height 2 all the way to the ground, that is 24 meters. Okay, so just keep in mind, try to remember, are you figuring out height above the roof of the school or height above the ground? In this case, we're finding height above the ground. Let's see if I can squeeze B in here as well at the same time. For B, I need to know something about, I'm looking for, let's say, this V3, which means I need to know one other thing. I need to know H. Remember, we're saying H down here is 0. For part A, I went from position 1 to position 2. In part B, we're going to need to decide where are we going to go from and to. I'm going to go from 1 to 3. Okay, so I'm going to go from 1 to 3. So E total 1 is equal to E total 3. Okay, so that's how I'm going to do it. You could go from position 2 to position 3. That will work as well. But I wanted to show you that we don't need to go to that middle position. So if I didn't ask you part A of the question, if I just asked you part B, you can go directly from this position 1 here to this position 3. Okay, so I'm going to write out this whole thing again. And I'm going to call it over here V3. Okay, just because we're using the labeling from this position down here. Same as we always do, we can cancel out those masses. V1 is 13. We saw this these numbers right up at the top there. H1 is 15. Remember, H3, or final height here, is 0. So I then end up with this. Oops, I forgot my squared there. Don't forget those squareds. The left-hand side, we saw this right up here at the top. Okay, so the left-hand side, 231.5. That's kind of the nice thing about going from 1 to 3. And that is 1/2 there. So this number, 231.5 times 2, and then square root of that answer. V3, 21.517. V3, we should throw little approximate signs in here. 2 sig digs, it's about 22 meters per second. They asked me for velocity. Keep in mind, when you do this, when you use conservation of energy, this V that they're giving you right here, or the V in this conservation of energy, is actually a speed. But I know what direction this thing is going, right? It's got to be going down before it hits the ground. So just keep in mind, when you do any of these questions, do double check what it is that they ask me for before you kind of sort of write your final answer or whatever. Make sure you're actually answering the question. In this case, velocity, not just speed. All right, one other question. Work is energy. Remember we talked about how work is a transfer of energy? If I do work on an object, I give it energy, or I change the object's energy. You could say it that way. So another way that we'll often see this is work is equal to change in total energy. Okay, so this is what some people call work energy theorem. In this case, we can say work is equal to change in total energy. Now that total energy, remember, so just remember, let's say it over here. Remember, total energy, let's say E total, is actually kinetic energy and gravitational energy. Let's say total energy 1. If I've got a change in that energy, I have to consider what's the change in kinetic energy and what's the change in gravitational. So when I write this, I'm actually going to say work is change in kinetic plus change in gravitational energy. What that means, this is going to blow your minds. You guys ready for this? Anytime it is delta anything, so this little delta sign means final minus initial. Okay, so that is the change in kinetic energy. We also have to consider what's the change in gravitational. So again, final minus initial. Look at that glorious equation. Typically, as we do something like this, when we talk about the work done, this is the work done by like an applied force. So this is Winston pushing this go-kart, Jill and the go-kart, I guess. In this case, what we've got going on, let me just draw a quick little picture in here. We'll slide this in. What we've got is we've got some sort of a go-kart. I'm not going to be much of a go-kart drawer here. Maybe Jill's inside here. You can kind of picture her sitting in there, and Winston's back here pushing. What's happening is V at this position is 2 meters per second. Okay, so it's already in motion. The go-kart's already moving. He pushes it for a while, and at the end of this push, the go-kart is now going 7 meters per second. Remember, when we're going to use this conservation of energy stuff, we kind of always have to consider what about height 1, what about height 2, stuff like that. This thing, it doesn't sound like it's going up a hill or anything like that. It's just on level ground. So I'm going to call this lowest height right here. I'm going to call this height equals 0, which means height 1 is 0 and height 2 is 0. Even if it wasn't 0, even if it was like this one is 10 and this one is 10, they're going to be the same on both sides. When we do this height 1 and or height 2 and height 1, when we sub into here, we're going to get the same values regardless of what we choose as height equals 0. which means those heights are going to cancel out, or those MGH terms are going to cancel out. Okay, so if that makes sense, awesome. If that doesn't make sense, if you're kind of like, what, ask me in class, but I'm going to call it height equals 0. I think that's sort of the easiest way to sort of see this. I'm going to take those values and I'm going to sub into kind of this equation that we've got up here, this equation, this whole big work monstrosity. Okay, and as I sub that stuff in, the work that he does then is 1/2, let's see, mass was 45. Remember, it's V2 first, so it's this number over here. So V2 is 7 minus 1/2, 45, and 2. And again, don't forget to square those things. This H2 is 0. This H1 is 0. Those things both cancel out. That whole second half cancels out. Okay, so I don't need to write anything over there. So we've got 7 squared times 45 times 0.5. Wait a second. Something seemed fishy there. 45 times 49. Yeah, okay. So work is 1102.5 minus 0.5 times 45 times 4 is 90. Work done, 1102.5 minus 90 is 1012.5. Almost looks like the same number, joules. This is not our final answer. This is not what they asked me for, right? They wanted to know what average force does he push with. But remember, we also know that work is, okay, so let's say over here, and we know that work is FD cos theta. Okay, so we can sub into this thing as well. We just figured out the work is 1012.5. This is the applied force. This is what we're looking for. He pushes over a distance or a displacement of 4 meters. So kind of picture from the front of the car to the front of the car. This is 4 meters. Let's say D equals 4 meters. Okay, so we know displacement is 4 meters. We also know this. It looks, or it sounds like from the question, we have to interpret this a little bit, but it sounds to me like he's pushing forward and the displacement is forwards, which means the angle between those two things is 0. Okay, so we're going to get cosine of 0. And remember, cosine of 0 is just 1. Okay, so we're going to just divide both sides by 4. And we get this applied force is 253.125. Applied force then for 2 sig digs, approximately 250 newtons. Or you could write it in scientific notation, 2.5 times 10 to the 2 newtons. What average force does she push with? Or actually it's he. I think it's Winston that's pushing. Anyways, what average force is being used to push on this thing? This thing right here. Okay, so this is actually the final answer. Average force. There's the answer. Whew. All right, there's a lot of solving. Good luck.